We now demonstrate the basic features and functions of our Visual Causality Analyst. The first interactive framework for visual causal reasoning. By clicking Import Data and select Data File, a variable type selection window will open. User may indicate the type of each variable as either numerical or categorical. In this example, only origin is a categorical variable. Then by clicking OK, all data is loaded. We firstly keep all variables being selected and click Layout Causality. Then a causal graph is generated in the causal graph view. In causal graph, vertices correspond to variables. Colors of a vertex encodes the type of variable, blue for numerical and yellow for categorical. Each yellow vertex may correspond to multiple dummy variables. When clicking on a vertex, regression analysis result targeting the variable will expand in the regression analysis view. We see here origin has two dummy variables, origin 1 and origin 2 in this regression model. An edge links two variables in terms of their causal relationships. The direction icon, colored arrows, on an edge encodes the direction of the causal relation, going from cause to effect. Green arrows mean positive relations, red arrows encode negative relations, and a yellow arrow shooting from or to a categorical variable corresponds to multiple relations between the target and dummies of the categorical variable, which cannot be simply described as positive or negative. For example, here we see displacement is a positive cause of weight, which means if we can artificially rise the displacement of a car, the car's weight will increase. Also we see weight is a negative cause of mpg, which is miles per gallon. This means increasing a car's weight will increase its oil consumption. Origin is a categorical variable pointing to mpg. That is to say, a car from certain origins may have a lower or higher preference on mpg. Also, we see that the opacity of the edge from origin to mpg is much lower than from weight. The opacity of the edge encodes the amount of change that is exerted by the cause onto the effect, which is measured by regression coefficients. A more visible edge has a stronger effect, thus origin is a weaker cause of mpg than weight. We can enhance all the edge opacities to make them more salient by sliding the edge opacity slider. We can also filter those edges corresponding to weak causal relations by sliding the edge filter slider. Now we can see by setting the regression coefficient threshold to around 0.4, origin and model year are independent from all other variables. Also, horsepower is no longer a direct cause of weight. If we only concern the causal relation related to mpg, we can hide all irrelevant variables and relations by deselecting them on variable list. Then relay out. We now get a chain of causal relations that's strongly related to mpg. Also, only visible variables are involved in regression analyses. Our framework also provides a suite of interactive tools for modifying the causal graph with visual feedback. For example, we can delete the edge from horsepower to time to 60 mpg by clicking on the edge. Then all available operations on the edge are lighted in the control panel. Here we click delete, then the edge is gone, and we see the arrow from weight to time to 60 miles per hour turns from green to red, which is the impact of our edge deletion. Going back by reassigning the edge then delete it, we can observe the change again. Here we can highlight some edges by clicking on them. Then clicked edges will be filled with its arrow's color. Also, the regression analysis view representing the regression model that contains the clicked edge is expanded, and the coefficients of the edge corresponding are highlighted, to make them salient for users. Here, as the target variable mpg is a numerical variable, our framework will conduct linear regression analysis automatically. For models targeting categorical variables, logistic regression analyses will be applied. In this example we see all mpg's predictors but one are significant as their p-values are small. Also, the r-square coefficient and f-test value are quite large, which indicate such a model has great goodness of fit. We can also use such tools to test hypotheses. Suppose one makes a hypothesis that displacement could be a direct cause of mpg. We can simply select displacement as cause and mpg as effect, then click assign. We get a causal graph where displacement is a direct reason of mpg. The newly added edge is highlighted. We see here the regression analysis is fed back at the same time that displacement is now a predictor of mpg. But the p-value of displacement is 0.399, which is too high. Thus we should reject the hypothesis and displacement should not be considered as a direct cause in this model. Then we can mark it unknown. Or simply delete it. In each step, visual feedback is provided and regression analysis is updated. The generated causal graph, as well as the regression analysis results, can be saved for further demonstrating.